price, our price P related to units sold, which is X, was given as price is equal to 1,000 minus 4X. And thank you. And what we are looking for is, sorry, clicking on things. We are trying to maximize revenue. So if I'm trying to maximize, no matter what sort of optimization problem I'm working on, whatever the thing is I'm trying to maximize, that's what I have to come up with an equation for. And for every optimization problem, that's okay. The calculus could be challenging or messy in terms of the algebra, but I would say that the conceptual challenging part of any optimization problem is that you have to come up with the equation yourself. There should be enough context in the problem for you to do it, but you have to come up with the equation yourself. So if we're talking about revenue, revenue is all of the money that I'm bringing in. Revenue is the price I'm selling at times the units that I've sold. So if I'm selling them at $10 each and I sell 20 of them, then the revenue is the money that I bring in. It would be the $10 times the 20 units I sold, which means our equation here for revenue as a function of X becomes that price function 1,000 minus 4X times X. Once you've got the equation, the calculus part is straightforward. I take a derivative, I set it equal to 0, test those critical points. I'm going to let you all do that part. Take this derivative, I get 1,000 minus 8X, and setting that equal to 0, if 1,000 is equal to 8X, I can divide it by 4, get 250, divide that by 2 again, so 125. Now, one of the things that is probably important to think about is what are possible values of X. So X is the number of units sold. I definitely cannot sell a negative number of units of something. So unlike rectangles, where I was making the argument that the rectangle doesn't exist when one of the sides is 0, I'm going to go with we could sell none, right? That is a possible outcome, probably a terrible business venture, but it could happen. So my lower bound is certainly that X could be 0. But there's an upper bound as well. And if you think about this, because P is the price, I don't want the price to get negative. That is also a bad business decision. So if I look at this equation, I'm going to say that X being 250 is for sure my upper limit. Because in order to sell 250 of these products, I would have to drop the price to 0. And that just doesn't make sense from a business standpoint. So X should only be considered between 0 and 250. Well, the value that we found is between 0 and 250, so we're good there. But we should show that that is actually a maximum. 2 options. If I go second derivative test, then I'm going to find that second derivative of the revenue, which would be -8. That means we're concave down, so I know that it's a max. If we were going first derivative test, then I'm going to think about that first derivative. I am only going to consider from 0 to 250. But I could plug in 1, and then I'd have 1,000 minus 8. That's definitely positive. So I'm going up. And I could plug in 200. And 1,000 minus 1,600 would be negative, and I'd be going down, which also shows that it's a max. In terms of answering the question, I don't remember if it asked us for the revenue or the number sold. So just to be safe, I know that our max revenue, I'm going to take that 125 and plug it back into our revenue equation. So our maximum revenue here would be 1,000 minus 4 times 125, all times 125. And our optimal units sold is 125. There is a request in the chat to do test examples of differentials. So I don't know if that means from Babson's practice exam, the differential problem, but let's do that. Questions about this before I flip a page? What do I say? Question, yes. Oh, it asked for the optimal price. Okay, so I said optimal units sold, so thank you. Let's find that. Great, so that part we did, the 125, that's how many are sold. But our optimal price is us plugging that back in where it says price equals. So price equals 1,000 minus 4 times 125. 4 times 125 should be 500. So my optimal price would be 500. For starters, I know it's an optimization problem because we've been asked to find the largest of something. So I know we're talking optimization here. Since I was asked to find the largest area of this shape, I need to start with a formula for the area. And personally, I think I'm going to need a picture to come up with a formula for the area. So let's kind of wrap our head around it. We're cutting corners off of a square. So I'll start with a square. And then we're cutting corners off. So we're removing those corners. So I would say in general, my area would be like the square minus 2 of the triangles in terms of their areas. And well, I got to start somewhere. So I think I'm going to call the sides of the square X. So my area of the square would be X squared. But I'd still have to figure out what was going on with the triangles. So I'm going to come in and say that this part of the triangle is Y. And for sure, if I do that, then writing the area of my triangles is pretty straightforward because the area of it, I'm going to have 2, and then the area of the triangles is 1/2 the base times the height, but they're 45, 45, 90 triangles. So that is a y. So I'd have 1/2 y times y, which would work out to be x squared minus y squared. And I look at that and I say, oh darn, I have too many variables. I sure hope we know something else in the problem. And that something else in the problem is usually a number. And the only number I've got in here is that 4 inches. So now I've got to come up with an equation for the perimeter of this shape. Good times. So if I'm thinking about this shape, we've cut the same size corners off here. So this side and this side and this side and this side should all be the same. It should be that x minus the y we cut off. So in terms of our perimeter, I know these sides, I'd have 4 of them, and it would be x minus the y we cut off. Then I've also got these diagonal bits. And I know that for those diagonal bits, I'm looking at Pythagorean theorem. So if I called that c for a second, I know that c squared would be equal to y squared plus y squared. Or c would be equal to the square root of 2 times y. So my perimeter would be 4 of these plus 2 of my square root of 2 times y. Also, if anyone thinks I've made a mistake, please stop me before we keep going because it already looks gross, but I think it's gross. Well, in terms of kind of process on an optimization problem, I need to eliminate either the x or the y using this other equation that was equal to a constant. I've only got one thing with an x in it, and I've got 2 things with y's in them, so I'm going to choose to solve for x. It shouldn't really matter. I'm just going with it. So if I rearrange this, I've got 4 is equal to 4x minus 4y plus 2 square root 2y. So I can say 4 plus 4y minus 2 square root 2y is equal to 4x, or x is equal to 1 plus y minus square root of 2 over 2y. And take that whole thing to plug it in for x. Which means that the area function that I would be trying to optimize here is that my area is equal to 1 plus y minus square root over 2, square root of 2 over 2y squared minus y squared. Normally, oh, and then once we have an equation, we can take a derivative, set it equal to 0, hope life works out. Normally, I'm always like, oh yeah, let's multiply stuff out so we don't have product rule or chain rule or something. I'm not going there this time. I actually think we're better off just using the chain rule to take that derivative. So I'm diving into chain rule here. Bring my 2 down, and I've got 1 plus y minus square root of 2 over 2y times the derivative of the inside. The derivative of 1 is 0. The derivative of y is 1. And then I'll have minus a square root of 2 over 2 minus 2y. Now it looks a little bit gross, but it is actually just a linear equation, meaning all of my powers of y are equal to 1. So even though it looks gross, it should be doable. Should we keep fighting through the algebra, or are we like, yeah, we could do it from there. It's messy, but it's algebra. Does anyone want to see me finish it off? Yeah, okay. I got some head nods. Let's go ahead and finish it off. I have 3 things that are multiplied together, so I can choose which of these 2 to distribute my 2 into. I'm going to go ahead and distribute it to the first one. By the way, I can't distribute it to both, or I'd be multiplying by 4, not by 2. So I'm going to distribute my 2 in to that first part and end up with 2 plus 2y minus the square root of 2y times 1 minus square root of 2 over 2. I don't know. Maybe we should get a common denominator on that. Multiply that by 2 over 2. So I had 2 minus the square root of 2 all over 2. That would have maybe been smarter to do from the beginning. I don't know. Minus 2y is equal to 0. I don't like this any better. I'm changing my mind. Because I'm going to have to multiply it in. I think I'd rather multiply this in. So I'm going to have 2 times 1, which is 2. 2 times negative square root of 2 over 2 is negative square root of 2. Then I'll have 2y times 1. And 2y times negative root 2 over 2 is going to give me a negative root 2y. Then I'll have a negative root 2y and a positive square root of 2 times square root of 2 is 2 over 2. So I think that's just plus a y, and then minus a 2y is equal to 0. Combine like terms. Gonna leave my y's on the left-hand side and get my numbers onto the right-hand side. So on the right-hand side, my numbers are that 2 and the negative square root of 2. So I'm gonna have square root of 2 minus 2. On the left-hand side, I've got a positive 2y and a negative 2y. Sweet, those are going away. Got this positive y, and then 2 square root 2y. I can factor a y out over here and have 1 minus 2 root 2. And over here, I've got root 2 minus 2. Messy as it may be, I'm going to get y is root 2 minus 2 over 1 minus 2 root 2. I am so sure that there's like some magic that makes that look prettier, but I am really, really, really not going to worry about it.